All right. So for the first half of class today, we're going to be talking about 4.3 in our textbooks, okay? So we're going to go through what we know, what's new. We're going to walk through an example together, use that to really nail down some vocabulary. Then we're going to go through a few examples to make sure that we really understood not just the vocabulary, but how to apply it, all right? So let's get started. What do we know so far going into section 4.3? Well, we know that a parabola has something called a vertex. And I'm wondering if someone can either in the chat maybe describe what a vertex of a parabola is before we move on, just to make sure we're all sort of on the same page about that. Yeah, it's like the turning point, the pointiest part. Okay. And so if we think about a parabola, we know that we might have one that's sort of facing up like this. We could also have one that's facing down, but at the end of the day, our vertex is sort of this point here where it stops going down and starts going up. Okay. And then that's one that I feel fairly confident that we know. The second one, shapes of polynomial functions, I think might be a vague memory somewhere in that pre-calc experience that you had, where you had to sketch graphs of polynomials and kind of think about some patterns that you saw about them. For example, we know what a second degree polynomial looks like. That's just the quadratic. But then there's also a third degree polynomial that might look something like this. The fourth degree polynomial might look something like this. And hopefully you and your classmates had a chance to talk about things like end behavior and how many bumps there might be in the graph, or how many times it might cross the x-axis, that kind of stuff, okay? We're not going to go super deep into that, but what we're going to take a look at today is really thinking back to shapes of different graphs and how we can describe them really using calculus, okay? And so in our what's new section, what we're really going to be focusing on for this first half is something called extrema. So we want to know what they are, and we also want to know how we find these extrema. Okay, so we want to know what are extrema and also how do we find extrema. All right, so let's get started with this example right off the bat, okay? And so what I'd like us to do is take a look at this picture right here and notice maybe some points that sort of stand out more than others. And let's assume also for this picture that there are no arrows on the ends of the graph, okay? Meaning that I don't want to have arrows here, okay? They're not imaginary, they're just not there at all. So it's almost like I just took a snippet of a picture and this is it, okay? And so what I want us to do is for every whole number value of x, all right? So we're looking only at whole numbers just to make our lives a little easier right now, but it's okay if sometimes you're working on other problems and the answers are decimals or fractions. That's going to be okay, all right? But I'm wondering, in looking at this, what we want to do is consider whether something might be a local maximum, a local minimum, an absolute maximum, an absolute minimum, or none of the above, okay? And so I'm wondering if someone can maybe type into the chat what they think this phrase in particular means, absolute maximum. All right, so give that a thought in your brain, what does an absolute maximum mean? All right, we've got one idea here that is the highest point on the graph. All right, I would agree with that. An absolute maximum is talking about the highest point on the whole graph. And so in this particular picture, knowing that we're not looking at, there's no arrows at the ends, like what we see is what we get, where would we consider the absolute maximum to be? So in particular, tell me what X value might get you to the absolute maximum on this graph. X equals -4, okay? And so if we go over to X equals -4, we notice that that Y value is maybe like 40, 45, somewhere in there. And that is certainly the highest point on the whole graph. And so next to where it says X equals -4 in the chart, we're going to write that this is an absolute maximum. Okay. All right. In contrast to the absolute maximum, let's take a look at this absolute minimum. Okay. What can we change about that definition that Thea gave, that the absolute maximum is the highest point on the whole graph? How can we change that to describe what an absolute minimum is? Yeah, it's going to be the lowest point on the whole graph. Okay. And so again, sort of ignoring the idea of arrows on the ends, which X value do you folks think corresponds to the lowest point on the graph? Yeah, X equals -3, right? All the way down here. We've got a point that is lower than every other point on the graph. And so we can call that the absolute minimum. All right, now let's move on to some of the other terminology. Okay, so since we were just talking about an absolute minimum, what are some thoughts that people might have on what a local minimum is? Any ideas on what the difference between a local minimum and an absolute minimum might be? Yeah, exactly. All right. So when we talk about a local minimum, what we're really looking at is the lowest point in a particular region. Okay. And so if we kind of zoom in a little bit, all right, so I'm going to zoom in right over here. And do you see how at X equals 2, it sort of dips down a little bit? Okay. So right there at X equals 2, it sort of dips down lower than the rest of the area around it. And so at X equals 2, we can call that not an absolute minimum, but a local minimum. Okay. All right. Well, if a local minimum is the lowest point in any given interval, a local maximum might be something we consider sort of the highest point in a given region. And looking at this graph, I'm wondering if you can tell me where there might be a local maximum. X equals -1. Yeah. Right over here, we've got sort of a local maximum, like it's the highest point in that particular region. And I would say that there's one more X value that corresponds to a local maximum. Yeah, exactly. This one right here is the highest point in that region. It's just not the highest overall, but it's still what we would consider a local maximum. So if we think about some points on the graph that might attract our attention, those would maybe be the 4 or 5 points that we would say, hey, these seem to be a little bit more significant than the other ones. All right. But looking at this, I wanted us to kind of scan through every whole number value of x. And so if we kind of look at x equals 2, or -2 rather, that would be like somewhere here. Would we classify that as a minimum or a maximum? No, right? That blue point is clearly not that special in any way, unfortunately, okay? And if we go over to x equals 0, that point's not particularly special either. And this point right here, not particularly special. Okay. And so for the non-special ones, we don't have a special name for them. We just say that they're neither. They're neither a maximum nor a minimum. So we can say these are neither. Okay. And so I think with this particular graph, we're able to sort of clarify the differences and similarities between absolute and local and minimum and maximum, and sometimes they're just not that special. Okay. Are there any questions about example number 1? Not at the moment. Great. All right. So let's move on to example number 2. Okay. And so for example number 2, it says draw the graph of f of x, which has the following characteristics. Okay. It is continuous. All right. And I only care about from x equals -4 to 4. I don't care about the whole graph. Let's just look at from -4 to 4. Okay. And I wanted to have the following properties: an absolute maximum at x equals 4, an absolute minimum at x equals -1, a local maximum at -2. Okay. So take a moment. I would start kind of sketching in your notes what those 3 things might look like. All right. And this last one here, critical point that is not a maximum or a minimum at x equals 2. Okay. And we're going to kind of save that last one. But what I'd like us to do is I'll set up maybe a few grids here. Okay, maybe like 3 different ones. Each hash mark along the x-axis is counting by 1. So that way we can get all the way to 4 and -4. All right. And the y-axis is intentionally not marked. All right. And what I'd like for us to do is take a moment and sketch in our own notes what it might look like to have a function that has an absolute maximum at x equals 4, an absolute minimum at x equals -1, and a local maximum at x equals -2. All right. And we'll figure out how to do that last criteria in a little bit. Okay. Now, if anyone feels like they've got a good sketch going on, I wonder if we could get maybe one volunteer to sketch on the first graph and a second volunteer to sketch on the second graph. All right, so we're just going to go with 2 volunteers for right now. All right, I see 1 individual on the first graph. If we could get someone else on the second graph, and we're going to leave this third graph for us to kind of complete the picture when we're talking about this critical point piece, okay? Got a few dots over there. It's been connected. Any thoughts on a second variation? Maybe another individual who's got a variation that they could draw on the second graph right here. All right. Well, since there are no other volunteers right now, let's just kind of take a look at this graph. And then I'm wondering, so for some of us, we might be sitting here saying, well, I don't really know what's different because she seems to have gotten the points where they should be. But one thing to think about is that where the highest point is and where the lowest point is could certainly be different, right? So perhaps we have a graph that maybe looks like this, that the highest point, that absolute maximum, is a little bit lower than where Thea had drawn hers, right? And maybe that absolute minimum is somewhere that is a little bit higher than where her absolute minimum is, right? And so that's one thing to think about as we're drawing our pictures, that the Y value itself, like the number of the Y value, doesn't actually matter. Rather, we're thinking about how do the points relate to each other, okay? Now, if I wanted to draw a local maximum at x equals -2, would it be okay to put my point up here?
No, because it's higher than your x value, or x equals 4 point.
Yeah, exactly. This point is higher than that point, and that can't be true if it's only a local maximum. Okay, so once I sort of establish the local max and min, I might need to be really thoughtful about where I put my other points. Okay. Now, maybe the graph looks something like this. We've got a local maximum here, and then it sort of goes down. It's a local minimum. All right. And then if I didn't have that last piece of information, the critical point that is not an absolute minimum or maximum at 2, then I could just sort of connect these however I want and call it a day. Okay. And so even though some of the characteristics about these graphs are similar, the way they look is actually a little bit different, okay? And that's something that in your homework or on exams, if I'm asking you to sketch a graph, there's so many variations. I want you to think about like what could be changed, what might stay the same, all right? But let's get to this last criteria here. So the critical point that is not a maximum or a minimum at x equals 2, okay? And so a critical point, which is something we're going to define on the next page, but we'll kind of talk it out right here. A critical point is a point on the graph that has a slope of 0. Okay, let me say that one more time. A critical point is a point on a graph that has a slope of 0. If I look at the blue graph that I drew, and I looked specifically at x equals 2, is the slope there 0? No. Okay, it's not. This slope right here, that's not 0, right? What does the slope of 0 look like? Yeah, it's going to be a horizontal line, right? And if I look at this graph right here at x equals 2, that's not a slope of 0. It's got more kind of like a positive slope here, okay? Now, one thing to clarify is that it is not a maximum or a minimum. So how do I draw a graph that has a slope of 0 at 2, but it's not the highest point and it's not the lowest point? Right? Anyone want to give that a go on the last graph? So go ahead, if you think you might have an idea, sketch some points or plot some points, and then maybe kind of connect them in a way that's different from what I did and what Thea did, where at x equals 2, we actually have a slope of 0. Okay. Oh, all right. Let's go through this checklist and make sure we've got all of those different criteria satisfied, okay? So we've got a local maximum at 4. I would say yes, right? Ethan's got a maximum there, and it is indeed the highest point of his entire graph, okay? An absolute minimum at x equals -1. Sure looks like there is the lowest point on the whole graph there. So I feel really good about this point and that point. All right, the local maximum at x equals -2. This could be a little trickier for me to draw, but that looks to be like the highest point in that region. So I'd say yes, that is a local maximum. And finally, a critical point that is not a maximum or a minimum, just a place that has, a slope of 0, like maybe it's just kind of hanging out there for a little bit. And I would say right here, yeah, that looks like it's flattening out a little bit. And I would say a slope there might be close to 0. Good. Okay. All right. So if we think about ways to have our vocabulary here, I think that one thing I could ask is certainly, how do you label a graph? That's one way to ask that question. But another way to ask that question might be to say, hey, I'd like you to draw a picture that represents certain pieces of, or certain pieces of vocabulary. Okay, so as you're sort of studying, you want to make sure that you're able to not just label a graph, but that you can also draw one as well. Okay. All right. So let's get some definitions down. Okay. So if we think about the absolute maximum and the absolute minimum, which we talked about earlier, an absolute maximum we can describe as this, okay? It is the x value with the highest, or some people might think about it as the largest y value on the graph. Okay. So it is the x value with the highest, or sometimes we say the largest y value on the graph. Okay. And if we modify this statement for absolute minimum, we could say that it is the x value with the lowest or smallest y value on the graph. And I think those two in particular are fairly straightforward because we're looking for the absolute, right? So it's got to be the largest one or the smallest one. What sometimes is a little trickier to visualize is that local maximum or the local minimum. And I think Thea gave a great definition earlier. We could say it is the x value with the highest y value in, that's not in the immediate area. Let's say region, in the immediate region. So the difference between an absolute and a local is that absolute is the whole graph, and local, we're really looking in just a small interval or a small region. Okay. And we could say for a local minimum, it is the x value with the lowest y value in the immediate region. Okay. Now, earlier, I said I want to define critical points as anywhere where the slope is 0. Okay. And that's going to be the first part of our description. Okay. It is perhaps the one that we use the most in calculus. All right. So we're going to say that a critical point, or all the critical points, are the collection of all x values where one of two things is happening. Okay. So where, number one, either this is true, okay, or this is true. Okay, so either the first derivative equals 0 or the first derivative is undefined. I know we had spring break, but one of the things I want us to really be comfortable sort of interchanging in our brains is we can say slope or we can say derivative. They kind of mean the same thing. Okay, so when we see somewhere where f prime of x equals 0, then we're looking at sort of something that looks like, visually might look like the top of a bump. So like right here, or the bottom of a bump, or it might just be a place where something sort of flattens out. Okay. Anywhere on a graph where that slope is 0, that is a critical point. Okay. But in contrast, we want to consider a case where maybe that first derivative is undefined. And what does that look like? Okay. That tends to look like when we have things like this. So maybe a pointy part of the function. It's not smooth. So the slope on one side is one number, the slope on the other side is another number, and it changes so drastically in that moment. Okay. And so at those points, we say that the slope is undefined or that the first derivative is undefined. Okay. Another way to phrase the second one is someone might say that a function is not differentiable. And not differentiable just means that the derivative is undefined. Okay. So before we go on to talk about an important theorem, are there any questions about the vocabulary so far? What about a vertical slope? Okay, that is another way that we can talk about things that are undefined. Okay, and we're going to see that in the picture below in just a second. All right. So here is an important theorem. Okay. So when we think about what this says, we want to be really careful about the direction. Okay. In particular, this part that I'm going to underline in the purple has to be true. Okay, so if the stuff in the purple is true, then the stuff in the orange is true. Okay. So if F has a local extremum, okay, so it means that it has a maximum or a minimum at a specific X value. So we're going to call it X equals C, so that C stands for some number, okay? But if there is a local maximum or local minimum at C, and F is differentiable at C, meaning you can find the slope at C, then we know that the derivative at C is going to be 0. Okay. So let's unpack what that means in this picture. We've got 5 different pictures to look at. Okay. So in A over here, local maximum at C, that checks the first box, right? There's a local maximum at C. So this first part of the characteristic, we've got it. Now, is the curve smooth at X equals C? And the answer to that would be yes, okay? So what we've seen in the picture is that there is a local maximum and the function is smooth. And if both of those things are true, then you can automatically say that the derivative at C is 0. How could I draw this picture a little differently and consider a local minimum at X equals C and have it be differentiable at X equals C? What might that look like? Yeah, we could have the same graph, but maybe upside down. Okay, so it could even be over here. Oh. All right, where maybe C is right here. And the slope here at C is 0. So there's a local minimum that checks the first box, and it's smooth at X equals C, so it's differentiable. Then what do we know? We know that the derivative at C is equal to 0. Okay. But we have to be really careful that we fulfill both of these. It has to be an extrema and it has to be differentiable. If you're missing one of those, then it's not going to be guaranteed. Okay. So for example, can someone tell me why I can't say that f prime of c equals 0 here? Like which characteristic am I missing in that graph B? It's not differentiable, right? So let's take a look at the slopes that are happening here. The slope, and Natalia, this might actually be a really good answer to your question. The slope right here is vertical. And that we know that the vertical slope is undefined. That also means that f prime of c is undefined, okay? What's wrong with picture C? How come I can't look at picture C and say, oh, the slope at C is 0? Yeah, there are infinite slopes, right? So I could draw a slope like this. I could draw a slope like this. I could draw a slope like this. There's so many possibilities. Exactly. There's so many possibilities that we can't guarantee that it's going to be 0. So we say it's undefined. Okay. Now, what's wrong with question D or with picture D? Right? Picture D, and I would say also picture E, both of those are missing the extremum part. Like it's not the highest and it's not the lowest. And so the only time that we can kind of guarantee that our slope is going to be 0 is when we have both characteristics. Okay, we've got the extremum and we've got that it's differentiable. And so part of this is that this theorem is actually really important in sort of the work we do. But I think more than the concept of this, it's important for us to consider what does the theorem actually say? Like, what are the things that have to be true in order for these other things to be true? Okay. And that's sort of like a big picture math thinking skill that I want us to start to get used to, instead of saying, ooh, somebody said the word theorem and I'm just going to run away from it because the theorem sounds scary. Okay. All right. So let's finish up this section with 2 examples on locating the extrema. Okay. So we're going to take a look at example 3, and then we'll take a look at example 4. And so for example 3, I want us to consider a few things. All right. It says, write the domain of the function. Then find the x values of all critical points. Okay. After we do that, we're going to do some thinking to come up with one way to determine whether a critical point is a maximum or a minimum. And there was someone, I forget off the top of my head right now who it was, but someone asked an amazing question before break when we were looking at the optimization with like the can, like what's the least amount of material you might need, or we were looking at related rates, and someone was thinking about like, how do you know if it's a maximum or a minimum? If all you know is the slope is 0, how do you know if it's a maximum or minimum? And so I want us to start to think about that today. All right, so we've got a gross looking function, f of x equals 10x over 4x squared plus 1. How am I going to find the domain of this? or let's even back up. What does domain even mean? Okay. So it's all possible X values. All right. So domain is all possible X values. Okay. How do we think about that? Like, how do we even think about that if all we have is this gross looking equation? What are some strategies? Okay. So one way to think about domain, I think, is exactly what Ethan said here, which is let's think first, are there any values that don't work? Okay, sometimes instead of trying to write out all the values that do work, it's easier to think about which ones don't work. Okay, so the question we want to ask ourselves is, are there any X values that will give us an error if we input that value into the function? Okay, so that's the question we're trying to ask ourselves. Are there any X values that will give us an error if we input that value into the function? Okay. All right, so let's see, we've got some ideas here. A factor. Okay, so let's see, we've got f of x equals 10x over 4x squared plus 1. Okay, so factor that denominator is our idea. That's a good place to start when we have fractions. 4x squared plus 1. If that equals 0, anytime that equals 0, we're out of luck. Okay, so how did we factor that? Or rather, what did it factor into? Okay. So if we solve for x, we'll get x squared equals negative 1/4, and then x equals plus or minus the square root of negative 1/4. All right. A value for this? Okay, so this equals plus or minus 1/2. We agree, we disagree. See, one agree, you agree. All right, well, I'm gonna be the party pooper and disagree with all of y'all. Me and Megan. All right. All right, that right here, folks, this is an imaginary number, right? This is why we have to be so careful about our signs. This right here, actually, sorry, this part right here means that we're dealing with imaginary numbers. All right. Now, when we're thinking about domain and range, we're looking at real numbers, not looking at imaginary numbers. I could do that, but I'm not plugging in imaginary numbers anyway. I can't see those on a graph. Okay. And so we sort of have this inherent restriction when we're looking at domain that for the context of what we're looking at, we're working in the world of real numbers. Okay. And so if you wanted to simplify this over here, you better have an eye over here. All right. But to kind of push back on this, yes, thank goodness it's not an exam on this, but this is the kind of stuff that keeps coming up, right? And we want to make sure that we're really fluent in what works and what doesn't work, okay? All right, so are there any real numbers of x that give us an error if we put them into the function? Well, I would say since we only found imaginary numbers, it looks like all the real numbers work. Okay. And so in our case, our domain here, this particular problem is going to be all real numbers. Okay. Now I'm spending some time here because on your quiz this week and on the exam, I am going to be asking you to find domain. All right. So domain is not one of those things that continues to go away. Like you learn it once and you're like, oh, I know it's the X values. And oh, I got this weird function. I don't know how to find that. That's okay. Right. We want to continue to build on this toolbox of what it means to be domain and how do we know whether things work or not. Okay. So in some ways, yes, this is kind of part of what I'm asking is, do we know all these little small details about the math, even as we sort of move on from that particular class? Okay. So the domain for this function is all real numbers because any number I put in for x, we're going to get some value for y. Okay. You can also look at the graph to kind of confirm that it is indeed a continuous function. All right. But now that we know that the domain is all real numbers, we can sort of move on to this next piece of finding the x values of the critical points. Okay. Now, since this is our first question, I'm wondering if you folks can help me fill out this description that to find the x values of the critical points, what might I need to use? What steps might be helpful in getting us to the x values of a critical point? Okay, so we've got someone that says the y value is 0. Is that what a critical point means, that a y value is 0? Got another one that says that the derivative is equal to 0. Okay, I think these are two good points to talk about. Which one should we be setting equal to 0 if we want to find the critical points? Ah, I love the way you phrase that, right? When we say critical points, we mean the slope is 0. Slope means I care about whether the derivative is equal to 0. Okay, so we're gonna X that one because that's saying like find an X intercept. That's not what we want. But we will say, yes, we want to take the derivative and set it equal to 0. Okay. So let's grab our function and you folks tell me what rule or rules am I going to need to find that derivative? Yeah, we're going to need that quotient rule. And so we'll go ahead and set that up. We've got u equals 10x, v is 4x squared plus 1. All right, real quick, someone give me what du is. And maybe someone else tell me what dv is. Yeah, I agree. du is 10. All right, anybody else have an idea for dv, or the derivative of 4x squared plus 1? What do we got for that? Eight x, good, good, good. Okay, all right, let's put this all into our quotient rule here. And we'll get f prime of x equals, let's see, v du minus u dv all over v squared. All right, I found my derivative. What do I want to do with it? We're going to set that derivative equal to 0. All right, good, good, good. And that goes back to our strategy. We said we want to find critical points. Critical points are when the slope equals 0. So I got to find that derivative and set it equal to 0. Okay. Now, one super, super important thing for us to remember when we're looking at fractions. I think sometimes things like this look very intimidating. How am I going to solve that? That's so many letters and numbers. But one thing we really got to remember, this makes our lives so much easier, is that when we're looking to have a fraction equal 0, the only way to get a fraction equal to 0 is when the numerator equals 0. Okay, let me say that one more time. The only way to get a fraction to have a value of 0 is if the numerator equals 0. So in this next step, I'm not going to have a fraction anymore because I don't care about what the denominator is. I only care about what makes the numerator equal to 0. And that step right there is one that we use in a lot of different contexts, not just when we're working with rational functions where we have the fractions, but anytime we have a fraction, we want to think if we want the output to be 0, then we got to think about when is that numerator equal to 0. Okay. If you did this, I would say go back to algebra. Okay. You did not say that, so you can stay. All right, remember, every time we do something like that, right, we're saying like, let's see, 2 plus 7 divided by 2. What you're telling me is that 2 plus 7 divided by 2 is 7. If you just get rid of those, right? And even if it's squared, 2 plus 7 over 2 squared, you want to cancel one of those. You're telling me that 2 plus 7 over 2 squared is 7 halves. But that's also not true. You could put it into the calculator, but it's not true. Okay, so think about it with numbers. Anytime you got that plus or minus sign in between there, you really can't cancel out stuff unless it's a common factor for every single thing. Okay. All right, so let's deal with this numerator now. I'm gonna go ahead and distribute that 10. We'll multiply over here. We've got 40x squared plus 10 minus 80x squared equals 0. All right, so we've got negative 40x squared equals negative 10. I've got x squared equals 1/4. Oh. Can I take the square root this time? Because we kind of made a big deal about this last time, that we couldn't take the square root. Can we take the square root this time? Yes, it is positive. So yes, we'll get x equals plus or minus 1/2. Okay, and so what we found here is we found the x values of the critical point. All right, in particular, x equals plus or minus 1/2. If I look at the graph, I should get a slope of 0 there. Okay. Now, for the sake of time, I'll leave that graphing to you. You can graph that on your own time and think about, okay, do those X values look like they kind of flatten out? All right. But I'm wondering if we can sort of just think about this last part, which is explain one way to tell whether a critical point is a local maximum or a local minimum. How do we know? How do we know if it's going to be the top of a bump or the bottom of a bump? We just found them, but we don't know what they look like. So what are some ideas you have on how you could tell whether something is a local maximum or a local minimum? Okay, these are great ideas, great ideas. Okay, so I see some folks that are saying, let's take these values and plug them back into the original function. Okay, so if I plug it back into the original function and I get one y value that's higher than the others, you know that's a maximum, right? But if you get a y value that's lower, then you know it's a minimum. Okay. And then I see something about the slope. Okay, so if I plug numbers back into the slope, okay, maybe there's something about slope, or what's that other word for slope? Derivatives telling us how to find whether something is a maximum or a minimum. Okay. So we're not going to find this right now, but we will return to this idea on Wednesday. Okay, that we can think about how might we tell the difference. All right. Okay, so before we head on break, let's go ahead and approach one more question. We're going to write the domain for this function, and then we're going to determine the X values of the critical points. All right. So we said above that the domain is the collection of all X values that work. And by work, I mean I can plug an X value in and it gives me a number back out. Okay. So looking at this function, X minus X squared, that whole thing squared, what are our thoughts? What X values wouldn't work? Okay. Yeah, and Umar, you're exactly right. The domain here is all real functions, or all real numbers rather. And the reason why is because we have a polynomial function here. And polynomial functions have a domain of all real numbers. There's no number that it leaves out. Okay, it's only when we get to some of the weirder ones, like a square root one or a fraction, that we really need to think about, ooh, maybe there are some things that are going to give me a problem. Okay. Lucky for you, I left those for the quiz. So you could think about those more on your own time. Okay. All right, let's find our critical points. So talk to me about the process. Is the process for finding the critical points going to be the same as what we did before, or is it going to be different? Right, so that's what we did last time to find the X values of the critical point. Can we do the same thing again? Or do we do something different? What are your thoughts? Yeah, we're still going to be able to do that same idea. find the derivative, set it equal to 0. Now, are we going to use quotient rule? Yeah, we're not going to use quotient rule. We're going to use a different rule. Okay. In fact, chain rule, I think, is a really great one to use here. So some things stay the same. The concept stays the same. But some of the mechanics along the way might be different. Okay. And so that's, I think, one thing that makes this a little bit trickier is you have to know the concept, right? We got to know y prime equals 0, but how we find that y prime might be different. So we're going to say y prime equals 0. All right, so we're going to take our derivative and we'll get that our derivative is, let's see, 2x minus x squared to the first power times, what's the derivative of the inside piece here? One minus 2x, good. 1 minus 2x, and that's going to equal 0. Okay, so we're taking our derivative, we set it equal to 0. We didn't need quotient rule, but we did need chain rule. Okay. Now we want to see when this equals to 0. So it is actually the most beautiful thing in the world that it's already in factors. Check this out. 2 times x minus x squared times 1 minus 2x equals 0. Everything is multiplied together, so one of those things has to equal 0. Right? If you look at this problem and you start foiling out, you're just going to make a mess for yourself. All right. It's already in a place that is going to be easy to find the zeros because either x minus x squared equals 0 or 1 minus 2x equals 0. Now, this second one, I think, is a little easier to solve. I can say that 1 equals 2x or x equals 1/2. That's going to be a critical point. And how would I approach finding the critical point for this other piece, or that comes from the other piece, rather? How do we solve this? All right, maybe we could move the x to one side. That's one strategy for sure. Okay. What I am going to say, though, is let's be really careful about this. All right. Which is that if we did that, which I'll write in the red so we don't do that. Okay. So if we move that, we would get x equals x squared. How do we solve this? Divide by x, so I get 1 equals x. The problem with this, let's see what the problem is. Let's do the other way, which is let's factor. X, 1 minus x equals 0. What are my answers in the green? Okay. What's the problem with the method in the red? Yeah, we missed an answer, okay? So don't do this. Don't do this because you're going to miss a solution, okay? It is such a problem when we sort of divide things away. Sometimes we divide away one of our answers, all right? So it is in our best interest to keep things all on one side, set it equal to 0, and factor if we can, okay? So this particular function actually has 3 critical points. So 3 critical points. And they happen at x equals 0, 1/2, and 1. Okay. So 3 critical points. We've got 0, 1/2, and 1. We could, as folks suggested earlier, take each of these points, plug them back into the original function and find the y values that go with them. Or maybe there's something about slope and derivatives that might be helpful for us here. Okay. So that, folks, is 4.3 in a nutshell.